Welcome to section 13.3, Volumes of Solid Shapes. We are going to be covering the following topics and understandings. These are the standards, vocabulary, and concepts. So the volume of a solid shape is a measure of how much three-dimensional space the shape takes up. And as with area, there is a progression of increasingly sophisticated methods for determining volume, and then we'll actually develop those volume formulas. All right, to understand how to determine volume and the volume formulas, they must first understand what it means. So what does it mean to say that the volume of a solid shape is 30 cubic centimeters? It means that the solid shape could be made with a total of 30 1 centimeter by 1 centimeter cubes, allowing them to be cut apart and moved if necessary. So the most basic way to determine volume of a solid shape is to make the shape out of unit cubes and then fill the inside completely and then count how many cubes it took. And so although it may seem primitive, it's really important because it relies directly on the definition of volume, and that emphasizes the meaning for students. So even though they should know this approach, they need to move beyond it to more efficient ways for solving problems. But the first step in understanding how to determine volumes in other ways is to use those moving and additivity principles. So, okay, as with a regular shape, we kind of get those same ideas. If we move it rigidly without stretching or shrinking, the volume does not change. And if we combine it without overlapping it, then the volume will be the sum of the volumes together. And we've already used these before. So let's think about if you have a solid lump of clay. You could mold it into all these different shapes, but they're all made from the same volume of clay. So from that point of view, the moving and additivity principles, it's as if the clay was divided into pieces and tiny pieces, or a new shape was made with the same volume. And you can do the same idea if you have water in a container and you pour the water into another container, the volume of water stays the same even though its shape changes. And when we talk about shearing, we're basically just saying that we could, kind of slice this all up into little tiny thin layers, and we could slide it, and that would be that shearing process. And the Cavalier's principle says that when you shear a solid shape, the volume and the sheared volume are the same. And that makes sense because we didn't actually take away any volume, we just shifted the shape over. So we're going to develop volume formulas, but before we do that, let's just kind of recall the shapes. So the height of a prism or cylinder is the distance between the planes containing the two bases. The height is measured in the direction perpendicular to the bases, not along the slant. So notice here that the height is the same on that edge, but it is not the same in those oblique ones because we're not talking about the slant. It's got to be perpendicular. So we've got a lot of explorations here as we figure out the volume formulas. Let's start with this first one here. So if you have cubic inch blocks, that's great. If not, maybe using a computer program or just drawing some stuff out, go ahead and work on these and press play when you're ready to move on. So students are sometimes confused about the difference between surface area and the volume of a box. Explain the two concepts in a way that could help students learn the difference. So when we talk about surface area, we're talking about the surface or the exterior. And when we talk about volume, we're talking about the interior or the inside. So kind of explaining to students with imagery, with boxes, labeling, or using nets can help them distinguish the two. So to determine the surface area and the volume of a closed box, all right, so let me draw a closed box here. And we've got 5 inches wide, 4 inches deep, and 6 inches tall. So let's start with our surface area. So we know we're going to have two areas of those, right? We're going to have two 5x4s. We're going to have two, let's do the front, two front and back, so that's a 5x6. And we're going to have two, the sides, that is a 4x6. So when we calculate those all up, we're going to get 148 square inches, square because it's area. Let's talk about the volume here. Well, we know we're going to have a bottom layer that's 5x4. So we're going to have that 5x4 layer. And we're going to have that layer how many times? 6 times. So times 6, we're going to get a volume of 120 cubic inches because that's cubes that are going in there. Go ahead and give this one a try. Press play when you're ready to see the solution. And there we go. So now let's look at the formula for volume of prisms and cylinders. Remember that both prisms and cylinders have the same base on the bottom. So we've got our cylinders that have those circles or circular shapes, or we've got those prisms, right, that have the same shape on the top and the bottom. Doesn't have to be a rectangle, could be all sorts of different things. And the way we figure these out is we want the area of the base, and we're going to multiply it by that height, which makes sense because that's how many times we're going to layer those areas, right? That's how many times we're going to layer those areas. And it might be helpful to look at this here. We've got that base, right? Here's our base. And we're going to layer it however many height. The height tells you how many layers you're going to do it. So the height is your number of layers, and the area of the base is the number of cubes in each layer. So the volume formula for prisms and cylinders is valid for right prisms and cylinders and oblique ones because it's just sheared, right? Ooh, that should be a highlighter. Sorry about that. It's just sheared, right? Remember, we're just moving it. We're not actually taking away any volume. We're just shifting the shape. So we can continue to use that same idea. And I do encourage you to read these either in your textbook or pause these slides. Let's look at an example here. A cylindrical container has a base that is a circle of a diameter 8 centimeters. Okay, so we're talking about cylinders. And the base is a circle with a diameter of 8 centimeters. When the container is filled with 250 milliliters of liquid, the container becomes 2/5 full. Okay, so maybe when it's this full. And that is going to have it's 2/5 full. And it's got a volume of 250 milliliters. They want to know, how tall is this container? All right, so let's think about this for a minute. We know that the volume of this container is the height times the area of the base. All right, so what do we know? Well, we know that, let's look at just this cylinder, right? This is kind of like a mini cylinder, right? Just that kind of bit that's full. And we don't actually know this height either, right? We don't know this height. I'm going to call it height 1. We don't know that height. Let's just kind of look at that cylinder. Well, that little cylinder is 250 milliliters, and that height we don't know. But we do know the area of this base. Remember that the area of a circle is pi r squared, and if the diameter is 8, then the radius is 4. So it's going to be pi 4 squared. So that's 250 equals 16 pi times that unknown height, and we're just talking about this little height right here. And if I divide both sides by 16 pi, I get that this height is about 4.97. About. So I know that 250 is 2/5 full. So 4.97 is 2/5 of its height. So I can say, okay, we don't know its height. 2/5 of its height, of the full height, is equal to 4.97. Well, I can solve that by multiplying both sides by 5/2. And so I can find that the height is about 12.43, what are we talking about, centimeters. And so that is one way to find that height. And we'll pause there. These problems can be a little involved, and we'll come back and do some more examples.